Welcome to our physics presentation for Physics 212 Project 2. We're going to start with the background. The problem that we chose was the problem in which we are relaxing our massless string assumption and adding in strings with mass. But before we get to strings with mass, we have to look back at the massless string assumption and see why we were using it in the first place. In our old model, we had the massless string assumption because it allows us to assume the tension force throughout a string is constant. If I have two objects that are connected by a string, there's going to be two action-reaction pairs between the object and the string. And if we look at the forces of the string in the x direction, you have the tension on the string by object B and the tension on the string by object A, which is going to be equal to the mass of the string times the acceleration. But if the mass of the string is 0, then we can say that those two tension forces are equal, and thus we don't have to use the string in our calculations. We can just act as if those two objects are acting on each other. And this simplifies a lot of our calculations because we do not have to factor in the acceleration or mass of the string at all to our force calculations. However, there are a lot of limitations to this model. For example, if you have a situation where the mass of the string is not negligible, then you would have to account for it, otherwise you might get a number that is not correct. Some examples are a heavy electrical cable over a short distance, or a firefighter carrying a very heavy hose. In those situations, you need to account for the mass in order to solve the problem correctly. And so that is why we now have to adapt our model to account. Now that we have recapped why we made the assumptions in our old model, we can now look at our new adapted model. And in our new adapted model, we are going to assume that the mass of the string is not equal to 0. It has a mass, and we have to factor that into our calculations. Now, we know for this project, we are given that the mass of the density of the string is constant. That is, the mass over the length is uniform throughout the entire string, so we don't have to worry about any weird situations in which there is a lump of mass in the middle of the string, which would severely impact the calculations that we are able to do. Instead, we have a simplified version of a string with mass. Now, there are still some similarities to our old model. For example, there is still going to be an action-reaction third law pair between the string and any object it's connected to. If a string pulls on something, that object will pull back. It's just how the universe works. So we can still use that to problem solve. And the process of summing forces still applies. Even if the string still has mass, we will sum the forces, find relationships, and solve that way. But there are some pretty key differences. For example, the string is now going to have a force. It's going to have a gravitational force because it now has mass, and it's going to have a changing tension within the string. You can see that if we assume that the string has mass, we can no longer assume that the tension force is constant, and thus we can't equate tensions between objects that easily anymore. This is best demonstrated by a massful string hanging from a ceiling. At this point, you're going to have the force of gravity pulling down, but the tension force is only going to have to counteract the force of gravity at this point. The tension force here has to counteract the mass of this portion of the string, and this will be stronger. The tension force at the top has to counteract the weight of the entire string, so the tension force at the top is going to be bigger than the tension force in the middle or the tension force at the bottom. And so we can see that we're going to have this changing tension force, which is going to impact our calculations. And that tension force is going to depend on where we are at in the string, which will complicate our relationships and how we are able to solve problems. But it will give us a more realistic model that we can build off of.
Okay, now we're going to make sense of the equations. So here's an example. First, we have our string hanging from the ceiling. Here are some of the constants that we're going to use to make sense of our equations. L being the entire length of the string, M being the entire mass of the string, G, constant for gravity, M1 being a mass of a section of the string, and L being the length of the string going from the top down. So here's a diagram again. So you have L being the entire length, M being the entire mass, and times G being the force of gravity onto the string. and y, starting from the origin up at the ceiling, going down for the entire length. And here, when we're at the top of when the string's at the ceiling, and y is equal to 0, there is a net force of 0. So you have the entire mass of the string times gravity minus the tension at the ceiling when y is equal to 0 is equal to 0. So you get the entire mass of the string times gravity is equal to tension when y is equal to 0. Okay, now we're going to split the string up into sections. So over here, we have the section y. So now we have the overall length from the ceiling down with a length y. Then here's our free body diagram of this section. For the tension when y is equal to 0 going up on the ceiling, the force of gravity, m of mass, or m1, of the mass of the section times gravity going down, and the tension of the rest of the string below, which is T of y. So here's the equation for section 1. So we have our mass of the section times gravity plus the tension at length y minus tension when y is equal to 0 is equal to 0. So we get tension at length y is equal to tension of y length is equal to 0 minus mass of the section times gravity. But before we proceed, we must use substitution. So we must take our answer from earlier, when mass times gravity is equal to tension, when y is equal to 0, and we must use a linear density formula of your mass 1 is equal to the overall mass of the string divided by the length times your length y. So from here, we substitute these back in. So we get tension at length y is equal to the overall mass of the string times gravity minus your mass, the overall mass of the string divided by the length of the string times your section length y times gravity. From there, we can pull out your big M and G. So our tension of y is equal to mass times overall length of the overall mass of the string times gravity, then times in parentheses 1 minus your length of the section divided by L. Now this can make sense because as y increases and it approaches the entire length L, it would become mass times gravity times 1 minus 1, which that would mean that at the bottom of the string that there is 0 force tension, which that would make sense. Then when y is equal to 0, as we solved here, your overall tension is equal to your mass times your gravity. And for more sense making on it, we can derive sense making for it. So we get dt over dy is equal to negative your overall mass of the string divided by your entire length times the gravity, meaning that y is the only thing that can really change within this to alter our overall force tension of the string.
Okay. Now we're going to go over how our model of string with mass fits in with real world problems. To start with, we're going to look at a string that is on two fixed points with no tension. To start with, we have a massless string, and with this, the string will be floating because there's no force of gravity to pull it down. So we'll have a straight line across. With mass and with no tension, we have the force of gravity acting on the string. So we're going to get this bowl shape. This will help us with the sled and the pulley examples. For the sled, earlier in the year, we did a homework problem where a sled was being pulled across a frictionless surface by a man at a certain angle. For this, we know that there's a normal force acting upon the sled by the ice and the force of gravity acting on the sled. And for this, we knew that the normal force acting upon the sled plus the y component of the force of tension counterdicts the force of gravity. We can go into this now with the string with mass. We know that the angle here is going to be bigger than the angle without mass because we have to counterdict the force of gravity plus the force of gravity on the sled plus the force of gravity on the string, which is going to add weight. So since this string is not touching the ice, there's no normal force acting upon this. So this angle must increase to counterdict this extra weight added onto the force of gravity. And that is why we get a bigger angle down with mass instead of without mass. And for the pulley, to start with, we're going to look at the massless part. So we have a block M that is smaller than block B on a frictionless surface being pulled down through a pulley by block B. And we know that the section 1 of the string is shorter than section 2. So with mass massless string, we only have the force of gravity acting on block B to pull this. So we're going to have a constant acceleration down. But when we add mass to the string, we also get a force of gravity from the section 1 and section 2. So as this is getting shorter, there's less gravity acting upon this section than with uh, this section. Plus, we're adding force of gravity onto this section because the string is getting longer and adding weight. So as we get farther and farther down of this being added from this, we will get more and more acceleration.
All right. And now, to conclude our project, we're going to talk about the limitations of our new model. Because no model is 100% perfect, and even this model, while it is still more accurate, still have its faults. Because for this model, we assumed linear mass density, mass over length, completely uniform and constant. But what if it isn't? For example, what if the rope bends over itself? Or what if there's a knot in the rope? Both of these situations would start to mess with our linear density system. For example, here, there's going to be this large collection of mass at this location, which is going to impact the tension at that location. And in this situation, there is no linear x value. The x value here could have two tension values. It is no longer a true function. And so in these situations, we would need a more complex and nuanced model in order to account for these slight variations. And so that's one way that we can analyze our model. And even though it's really good, it helps us explain things like why ropes are concave, why we have to pull harder on a heavy rope in order to move something. We still have some limitations, and we have to remember those as we go forward and as we apply this model so that we can apply it correctly.